Okay. I think it's Friday. Hi, everybody. Happy Friday. I mean, welcome to my channel. Make sure to like and subscribe down below, I think. So this time I tried putting I guess I'm changing two things about my stream this time. One, I tried to put like an intro thing because, oh, happy Friday. Woo! I tried to put like an intro thing so that people could join before, and then it wouldn't be like, okay, I'm starting now thing. And the other thing is, I'm not wearing headphones today. Oh, thank you. I'm not wearing headphones because I realized that like I don't actually, I don't actually listen to myself when I'm doing this. So I thought maybe I don't need the headphones. But now I feel a little bit like I feel kind of naked without them. All right. Oh, I like that I have my YouTube analytics up here and we've got an average watch time of 36 seconds. So thank you. Thank you. Hello. Okay, so today I thought we'd do like we're gonna do more TenderJIT hacking today. But I'm changing another thing about my stream. I've decided to switch to like Robert's rules. So we're gonna do like where is the next thing? Next. No, give me keynote. There we go. No, that's not what we want. Play keynote. Okay. So first we got to start with old business. Oh, you want the mic volume up? Okay. Is this better? Hello, hello. Is the mic volume okay now? I will take that as a yes. Okay. Okay, so old business, and our old business is that I have OBS up. So last time we tried to get OptCare working, and it it didn't work. Like I ran into a bug at the last minute. So what I want to do this week is we're gonna look at like John Hawthorne was nice enough to pair with me, and we figured out what the issue is. So I want to look at the issue, and we can all see how I messed up. I also want to look at last week we discussed passing parameter types. Like, for example, if you have two literals like this, like 1 and 2, if you do like +1 + 2, we're able to know that like, oh, we have a 1 at compile time. So the JIT can tell, oh, we have a 1 here, and then we have a 2 here, and we can specialize the plus instruction so that it knows to do just adds on those integers. But unfortunately, types get lost. So let's say we refactor that out to a function, and like right here, we know the types in the caller, but unfortunately, the callee just gets these locals, and the locals don't know what types they are. So yeah, we'd really like to know, like in this case with opt plus, we have to go back to a slow path add because we don't know what the types are. And eventually I'd like to add multiple versions. So if we can tell at the call site, like, oh, we got ints this time, and then next time maybe we got, I don't know, strings or something, we can specialize the methods there. So it'd be cool if we could be like, okay, this call site is specialized for ints, and this call site is specialized for strings. Now let's move on to new business. So that was a couple weeks ago. New business is I want to look at some LLDB debugging. I was on Twitter, what do you call it? Twitter Spaces, and somebody asked a question like, "Oh, our process is blowing up. Like we're getting tons of memory, and we don't know where it's using tons of memory. Don't know where it is." And I suggested, well, you could tell the process to dump a core file and then inspect the memory of the core file and try to figure out what is chewing up all that memory. So I thought maybe it would be interesting if we did that. So make a Ruby process, dump a core, and then poke around in it with LLDB. And I think this is also important because as I'm hacking on TenderJIT, it's like my main way to debug stuff is with LLDB. So just a few commands that I'm going to use. I just wanted to put these in the slides so that people would like look at it and remember, like as a quick cheat sheet, I guess. So BT means backtrace. F, the F key, if you use F, it says like I can choose a frame. So if we look at a stack trace, I'm going to use these. P is just print. And then RP is Ruby print. So this one is a bit more interesting. Those previous commands all come with LLDB. But Ruby print RP is a like an extension that ships with Ruby, and you have to load it into LLDB. But I'm going to show that. Hi, Julian. Happy Friday. Woo! All right. And those all come in MISC, LLDB, cruby.py, which I'll show you in the command line here. I also want to look at tagged pointers. And then we'll look at passing parameter types, hopefully. So, all right. Let's look at the terminal now. Okay. So, let's see. Git presentations. I put like a test script in here. Here we go. And let me know if you want the font bigger or anything. I can bump that up. It seems big. Let's make it bigger. Bigger always helps, I think. All right. So let's see. There's two different, I think there's two different styles of debugging with LLDB. One is like you get a core file, your process crashes, and you want to debug it. And the other one is like you have a live process, and you're debugging the live process. So what I want to do first is take a look at let's make a program with a big heap, and then pretend that it crashed, and then try to inspect the heap and check out what's going on with the process. So I made this script in advance here. Big heap. Okay. No, let's bump this font up. Okay. Make Vim a little bit smaller. I don't know if I like doing this without headphones. Randall asks like Bybug. Yeah, kind of like Bybug, except that this is just debugging what the actual machine is doing. So what we're gonna do here is we got two classes. Let's try this out. We got two classes, foo and bar, and we're gonna make like a lot of objects. So this function just makes a ton of objects, and I put this one in here on purpose. This like object.new. And that's just gonna create garbage. So like, it's just gonna get collected, and then we'll never use it. And then we return this array. So we got a bunch of sub arrays here that we return, just different instances, and then maybe different strings of different sizes. So we'll make lots of them right here, and then it's gonna print out the process ID for the process. And then it's going to actually just like tell itself to exit. So you can send a segv signal to yourself, and that'll cause the process to crash. I mean, we could do it with kill, or maybe like your out of memory killer will do it. There's different ways for the process to crash, but we want to do it I want to crash on purpose. So we can just say like, hey, let's crash the process with the segv right here. So I'm going to do that. Shut off that thing. All right, so we can just run this. If we run it, it's gonna crash. So there we go, it crashed. And you can see actually let's read this. Let's read this first so we can kind of understand what the output is here. So the output of these crashes, when you read them, you'll see okay, here's our crash report. It died from a segmentation fault at some address. So this address is where it crashed. We can get kind of some information here about the stack trace. So you can see it died inside of the kill function, which makes sense because we just called process.kill. So that makes sense. And when we were on big heap RB line 15, so get some information there. It also shows you so this is the Ruby level control frame information. So that's like internals to the VM itself. And then here is like the Ruby backtrace. So this is a Ruby backtrace. This is a bit more low level. These are the machine registers. So what was inside, like what each register, the value of each register contained in the CPU. And then here you can get a C level backtrace. We're getting even more low level information. And then you can see like the script along with any other things that it loaded. Now, oh, and these are also the page mappings here. Now, one thing is like this didn't actually dump a core file, unfortunately. If you wanted to dump a core file, you need to make sure to set your U limit. So like if we do an ls in cores, there's probably nothing there. Oh, there's one there, but that's one that I was creating earlier. So like if we do this, if we run the program, it'll crash. But if you do ls cores, there's nothing there. So you need to do u limit minus c unlimited. I'm gonna bring this up a little bit because I'm afraid I'm in the way. There we go. All right. So you need to do u limit minus c unlimited, and that'll set the size of the core file it'll dump. So you can do that, and then when we run this, it'll crash, and it's gonna take a lot longer. So what's happening is the process is actually taking a snapshot of memory and dumping that memory out to disk. And what we're gonna do is just examine the contents of that memory. If it dumps here soon-ish. I think maybe you saw the, oh, there we go. Okay. So if we take a look at the cores, let's see, LH cores, it's kind of big, like it's 4 gigabytes. And you saw this was like a very small program. So yeah, make sure you got some disk space. So we'll pull this up. We're going to do LLDB, Ruby minus C, and then we just give it the core file. Let's see, core, whatever. All right, so we got our core file. We're in LLDB. And usually the first thing I do, like when I'm trying to debug problems like this, the first thing I'll do is I'll just ask for the backtrace. So you can see the backtrace here. And this is basically the same information that we saw in the crash report. But usually I forget what was in the crash report. So yeah. How do my eyes not burn while I'm looking at a light theme? I don't know. I like light themes. It keeps me awake, right? I'll fall asleep if it's a dark theme. Okay, so we crashed in here, error.c, and that's fine, but we knew that because we told it to crash, so that's why I crashed. But that's not why we're here. What we wanted to do is take a look at the contents of memory, so what objects were around at the time of the crash. And the way you do that is through object space. So like all Ruby objects are allocated out of object space, and we need to get access to object space somehow. And unfortunately, it's not just obj space or like RB, like you can't do like p obj space. It's not there. So if we go take a look, like let's go look at Ruby source. If we look at the GC and we find like, where is it? RB get like obj, what is it? Obj space. Can't even remember. So there's this thing, RB obj space. So if we look at RB obj space, what it's doing is it's saying like, hey, get the VM and then get the object space for that particular VM. So the idea is that Ruby is set up so that we could possibly have multiple VMs running. So we have to, like, the object space or the heap is per VM. So we need to go figure out like, okay, how do we get the VM? So I'm going to go jump to the VM function, and get VM just calls RB current VM. And if we look at that, it returns this Ruby current VM pointer. And that thing today is actually just a global. So if we go look at this, it's just a global. So yes, there are functions, so possibly we could have multiple, but it's just a global right now, and maybe like other things set to global or whatever, but it's a global. So let's grab this global, and if we go look in LLDB, we can get access to it. So do that. So there's our, like, there's the current VM. And if we do a star on here, we can see what's on the VM, and it's pretty big here. Pretty big. Like, here's our current reactors. And where is it? Actually, it's hard to read, so I'm just going to go back here. Let's go back. So what does RB obj space of do? It just says, okay, VM, give me the current VM, and then ask for the obj space, like the obj space thing on the VM. So let's do that. So if we do that obj space, there is our heap. So here is object space. Now, the next thing we need to do is the object space is actually divided into different. Okay, this depends on what version of Ruby you're using, but with Ruby Master and upcoming versions of Ruby, we're going to have different size pools. So you can say like, oh, I want to allocate a 40-byte object or an 80-byte object or whatever, some size of objects, and it's going to come out of different size pools. Right now, we only have one size pool of size 40, slot size 40. So we'll ask for the size pool, and we'll get the first one, and the first one should be slot size 40, and it has 31 pages in it. So let's take a look at that. Obj space. Well, what was that field? I already forgot. Man, I'm like pretty useless today. Size pools. Okay, size pools. Let's just do 0. And it's mad because of something. We don't want to do star on that. Just do that. And size pools has what? It has, okay, our slot size, pages, and the Eden heap is what we're interested in. The Eden heap is where all the objects actually live. So we want to look at Eden heap. So we'll do, I think, arrow. No. This is how trained professionals work. Just try it until it works. We don't want a star. Okay. All right, so Eden heap, and we're gonna look at pages, and this is kind of interesting. So pages is a linked list of all of the pages in the heap. So if we say like pages, let's try dot pages. Yes, okay, it's a linked list, and the way these linked lists work. So Ruby uses an interesting linked list structure. If we go look at let's go look at tag heap page. So if we go look at a heap page, you'll see here, oh, okay, each page has some slots, like the number of slots, total sizes, free slots, pin slots, final slots, blah, 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 right? Now, eventually, you'll get down to this part here, which is the list node structure. And this is actually how the linked list is stored and works. But the awkward thing is that, like, when we're doing a linked list, like let's say we have one page that points to the next page, that points to the next page, etc. It's not actually pointing to the head of the page. So it's not pointing here. It's actually pointing to here, to this page node itself. So we have to do some math on it in order to get back the head of the page. So like if we go look at like heap, what is it? Is there like a next page next, or like list next maybe? Yeah, there we go. Okay, so if we look at list next, you see like it takes this pointer to the pages. It takes the page itself, like what link we are in the list. So we have the head of the list, the link that we're currently at, and then the member of the struct, like where that is in the struct. So the idea is we look at the page, we get the next one, but then we have to subtract where the page node is. So let's go look at page node. So page node is here, and it's inside of a heap page. So let's go find the actual heap page. So we'll say pages.n.next, I think. Yep. Okay. So as I said, this address here is actually pointing into the middle of a page. It's not pointing at the head of the page. So we have to say, okay, we don't want this address. We want uint, well, actually, let's do this. You can do p offset of struct heap page, and then what is it? It's page node. That's what we want. Page node. So the offset of page node is 48. So this address here is 48 greater than the head of the page. So we have to subtract 48 to get back to the head of the page. So let's say like, okay, this thing, let's cast it to a u int pointer t minus 48. So that's the actual address of our page. And if we say like, okay, let's cast that to a struct heap page star. Ooh, is that gonna work? Yep, there's our heap page. And let's dereference it. Okay, I need more parentheses. There we go. Okay, so now we have our actual heap page. And we can see the first page is 40 bytes, or the slot size is 40 bytes, and we have 409 slots on this. This page has one free slot. Okay, that's nice. But like, what we'd really like to know is what data is stored in this page. So like what actual objects are in here. And this is where the LLDB scripts come in really handy. We have a heap. What is it? I think, well, let's just go look at the script. So if you go to the Ruby source and you look in misc LLDB cruby, these are the Python scripts for running, like for scripting LLDB. And if you go down to the bottom, you can see all the commands that it has. So like we've got here a heap page, like this thing, dump node, heap page body, dump page, blah, 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 blah. But here, like what we really want to do is I want to know what's on this page specifically. So we'll use the dump page macro. So let's go back to the terminal. We'll do, oh man, that's a very long command. Let's do dump page on this and see if it works. Yes, it did. There we go. This is like, can I widen this out? Okay. So if we go, like this is a list of all, actually I'm gonna make, sorry everybody, I'm gonna make this a little bit smaller so that we can fit it on one screen here. There we go. Okay, so this is a list of all the objects that are stored inside that one page. And you can see here, okay, we've got like a string, it's stored at this address and it has these flags, and you can see all the different types of objects that we have on that page. And this is the very first page in the heap. So we can see, we got a string, imemo, array, whatever, like all these different things. Let's grab one of these. Let's get this string here. If we take this address and we do RP on the address, we can see, oh, there's my there's my random string. So we were doing, let's go back. I'm surprised. Like I couldn't, when I was practicing this, I couldn't find those strings anywhere. I kept looking. So we're creating these like OMG LOL strings, right? So I found one. I'm very surprised. I didn't think I would find one. So we got one here. That's OMG LOL, and this is all of it. One thing that's interesting is like if you look at the output here, you can see what the encoding is. So we know that it's a UTF-8 string, and these bits are also important too. These bits are interesting. So L, if I remember correctly, L means that it's an old object. Promoted also means that it's an old object. M means that it's marked. So I forget what the other bits are here, but if there's other bits, they'll show up in here as well. I think there's like a U for uncollectible, but the different bits will show up in this box here. Let's see. What else do we have in here? Nothing else. This page is entirely full, and you can tell because there's nothing in, like, this free list index tells you where the object is in the free list for that page. Each page has its own free list, and none of these are in the free list. Oh, no, I'm wrong. Here we go. We have one right here. Here's a free slot. So it has one free. Well, I think we knew that, didn't we? Yeah, because I said free slots equals 1. Okay, good. There we go. There's our free slot. And we can get to the next, like, let's get to the next page. So I'm just going to do p, like, this command is super long, so I'm just going to do p that, grab this address, and we can be like, okay, p struct, like, struct heap page star, this thing. So that's our heap page. And then we want to know, what is it? We want to get to the next one. The next one is stored here on page node dot next. So we can say like page node dot next. And again, this is 40 bytes too far, or 48 too far. So we gotta like wind back a little bit because it's pointing into the middle of the next page. So we say, let's cast this to a uint pointer ptrt, and then subtract 48. And then this is our new page. And I'm gonna cast it to a void star so we get a hex, like a hex address. So this is our next page. So we can say like, okay, dump page blah, and then here is a dump of the next page. And I mean, this isn't like, you can go through this and like find all the objects in your heap doing this, and it, I mean, I guess it kind of sucks because you got to do all this math and then dump each page. But you can script it with Python, so I think it would be really cool if we had like a way to be like, okay, given a core file, I want you to produce a object space dump for that core file. It's something I've been imagining for a while. I just haven't had time to do it. But I think it would be cool if you could say like, give me a core, like, I don't know if all of you know this or not, but there's like that API that's like object space, ob_space.dump all, and it gives you a JSON, like a JSON heap dump of all the objects in your process. I think it would be cool if we had something like this, but it was just specifically for core files, so you could see what was in your process when it crashed. Okay. Oh, if anybody has any questions, like, please put them in the chat. All right. What else did I say I wanted to talk about? We got this. Oh, I guess let's look at an iMemo. So these are the different types of objects that are stored. Let's do RP, this one. So we got an iMemo here. Oh, this one's interesting. You can see what type the iMemo is. So instruction sequences are stored, like the actual instructions are stored as iMemo objects. And we can see what type that is here. And if we care about like the structure of this thing, let's go look in here. Let's go to tag iMemo iseq. Look for these. Nope. Don't care about that. Let's see if we can find something cool. Mark. Okay. So we can just cast that address to an RB iseq. So if we do like, I don't know, p RB iseq star on this address, get that. And here's our instruction sequence. Let's check out like, what is this? Let's do arrow body. This is the body of the instruction sequence. Let's do, what do we have here? So we can see, this is a block. So we can tell that this is for a block. This is a pointer to the actual instructions themselves, like the yarv instructions. Let's look at location. So let's do like dot location. Oh, nope. Body arrow location. Oh my gosh. It's this star. Okay, and then I want to look at, I think we want to look at like maybe path path let's see what that is. Okay, so this is the instruction sequence for some block that's inside of rubygems.rb. I guess let's look at the label. Can we look at base label? Base label. Yeah, so it's for register default spec. So we could be like, let's grab this. Let's go over here. And there should be a function register default spec here, and it's gonna be one of the blocks that's in here. I don't know which block it corresponds to because it looks like there's a bunch of blocks in this method, but I mean it could be any of these, like could be that. Let's see. First line note. I don't trust that. Let's look at label. What is a label? It's just no. Label. Block. Yeah, I don't know. Block in register default spec. So it could be any of these. Could be any of these. I guess we'd have to look at the line number, but calculating the line number is like not easy. So yeah, okay. That's neat. Right. Let's check out my slides here. I wanted to do okay, so we went over these. I want to talk about tag pointers. Okay. So one weird thing is like, code location has line number 1207. Oh. Thank you, Matthew. I guess it's not that hard. It's right here. Let's see. 1207. Okay. Oh, we got 2 blocks there though. So it's one of these. This one or this one. Okay. Column 47. So where is it? What column is this? That says 48. So I bet it's close enough. It must be this outer block. Interesting. That's awesome. Okay. All right, so I wanted to talk a little bit about tagged pointers. So another thing that I think may confuse people is if you notice, like, we say everything in Ruby is an object, but maybe you noticed as we were doing heap dumps in here, we see like imemos and strings. I'm not seeing any objects. Oh, there's a class. Like we got a class here. Let's do class. What is this? Repeat class. Right, we got a class, but we don't have any numbers. When do you typically use LLDB? Yeah, so I typically use LLDB when I'm working on Ruby itself or in this JIT project that I'm working on. But I mean, it depends. Like if it crashes, if the process crashes, or if there's some kind of C extension that breaks, I'll use LLDB in that case too. Okay, so none of these objects are numbers, which I think is interesting. So, like if you do the number, let's go back here. Let's go look at, why do I have so many buffers open? Let's do BU1. All right. So if we had a function that was like, I don't know, def foo, and we did like 1 plus 2, this doesn't actually allocate any objects. There's no objects allocated here. Actually, we could probably measure it. So if we do like foo, let's do object space dot stat colon total allocated objects, I think. Let's see. I hope that's right. It's probably not. Oh my gosh. doing some real live. Oh, come on. Stats. Where's did you mean? Object space. Oh, probably GC. Oops. Should know this. Ah, yes. Wow. So if we run that, okay, so there's our total number of allocated objects. So let's like grab this, x equals this. We'll call foo, and then print out the difference. So let's say like p, let's grab this again, p that minus x. So if we run this, oh my gosh, it's 1. Why is it 1? Oh, you know what? Probably the p did it. So let's do like y equals that, py. Oh my gosh. Anyone know? Inline caches, maybe? Try warming it up a little bit. Should be allocating 0 objects. Let's just return 1 and see what happens. Oh my gosh, come on. Is it the GC stat itself that's allocating the object? What is this? Ah! All right, anyway. Is X an object? No, it should just be an int. Total allocated objects. Yes, it's just an int. All right. All right. Whatever. Let's talk about tagged pointers, because that's actually what I wanted to talk about. So these numbers 1 and 2, like, I bet I could do. Now I'm starting to get distracted. I'm thinking I got to figure out what this object is that's being allocated, but that's not the point here. I wanted to talk about tagged pointers. I'm sure we could figure it out though. Like if I did this, what if I did this? What is it? No, okay, no, I'm not going to get into it. No. Okay. So we have tag pointers. Ruby has a system called tag pointers where instead of allocating an object, we detect that something is an integer. So for example, this number 1, when it goes over into Ruby itself, or into C land, into machine code, it's actually 3. And 2 is going to be what I can't do the math. 2 is going to be 2 shifted over 1 or 1. Oops. What is that? 2 1. Okay, 5. Right. All right. Yes. Rabbit hole avoided. Yes. So what this is doing is it's always setting the bottommost bit to 1. And if the bottommost bit is 1, then Ruby is able to detect like, oh, this isn't actually a heap allocated object. This isn't a real object. If the bottommost bit is 1, it's like, this is an int. Okay. And I'm trying to think of a good way to demonstrate this exactly. Oh, I know how. Like if we look at like if we look at the object ID, so let's do like 1.object ID, it's 3. So that's actually the encoded integer, the encoded number. So if we do like 4, here's our 9, I don't know, 4, 5, whatever. It's doing that math, so it can detect that the bottom bit is something, and the bottom sum bits are a special pattern, and based on that special pattern, we can handle it specially. And these are actually mapped out in gc.c. So if we go look at, let's look at this. Where is that going to be? Object ID, probably. The object ID method has it mapped out here. So let's look at the 64-bit space, because that's where we're looking. So false, like the literal false is going to be 0, true is going to be 1, 1, 0, nil is 1, 0, 0, undef is 0, 0, like 1, 1, 0. Symbols always have a 0 at the bottom here. Objects always have a 0 at the bottom here. And fixed sums will have a 1. So you can kind of see this pattern that's used. And where this comes in, like, oh, question. So is there only one way to know that a pointer is pointing to a primitive thing on the stack? You know by looking at the address of the thing. So if we go back to, let's pull up our LLDB here, grab, actually this was an object, wasn't it? Yep. Okay, so this number here is always going to be divisible by 40. So like, let's take a look at this and do, I'll bump this up. If we look at this and say like 2s2, we can see these bottom 3 bits are going to be zeros. So we just take a look at the address for that. So like, for example, if we did the encoded number 1, so 1.object ID, we'll see that that bottom bit is 1. So we know that it's not a heap allocated object. I think, will symbols do this? Symbol.object ID, maybe? Yeah, okay. So there we go. Like this is a 1 here, so we know that this is also not a heap allocated object. This pointer bit. Okay. So where this comes in, like, which is kind of interesting, we're gonna go over to TenderJIT now. What time is it? Aye. So if we have a thing, like let's say we have a method, bump it up. I really need to make like a thing for streaming. Oh, we don't want this. Let's do Aaron.rb. So let's say we have some method like this, like foo 1 plus 2, and right. Now let's say like, let's dump the instruction sequences for that, -- dump, Aaron. We'll see that we have, yeah, 1's not a good example. Let's do like 5. So we see we have a put object 5 and a put object 2, right? So in previous streams, I talked about how this is a stack-based virtual machine. So we'll push 5 onto the stack, and then we'll push 2 onto the stack, and then we'll call plus on this, and we get our value 7. However, when we're processing this with TenderJIT, like let's actually compile this method. So let's say like require we want JIT equals TenderJIT.new. So let's go take a look at the handler for this. Where's handle put object? Okay, so handle put object is going to compile the case where we have object literals, right? And this literal, like this is the literal that comes in. So if we print out the literal, p literal. So if we looked at the dumped instructions, we would imagine, oh, we're going to have a 5 and we're going to have a 2 when we compile this. But if I run this, what did I name it? Aaron. We'll see that it's literal 11, literal 5. And that's because we're getting that encoded value passed into us. So we can do, like, if we do what? If we shift it down 1 bit, we should get the original value. Yeah, there we go. So we got a literal 5, literal 2. So that's how Ruby is able to handle integers without actually allocating any objects. So we can see, like, we can also see this happen with strings. So let's do something here. Let's do, well, not tag pointers. Let's compare a tag pointer with a not tag pointer. So let's do, what is it? I guess they're all tagged pointers technically. It's just those bottom bits indicate the tag. Free, frozen. You all know what I mean though, right? 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 Okay. Let's grab this. Frozen string literal true. Okay. And then let's put in this. So we'll have hello plus 2. Is that gonna break? Ooh. Let's run it. No, yeah, it breaks. Okay, let's just do 2 strings. Okay. If we dump this out, wow, that's a lot of stuff. If we dump this out, you'll see that we've got a put object hello and a put object world. So this is like compared to the other one where we had a put object 5 and a put object 2, right? So let's do this. We'll print out the literal, and I'm gonna print it out in hex, and then I'm gonna print it out in binary. So we'll run the compiler, and you see here we've got 2 objects, and these bottom 3 bits are 0, right? Here's our hex for both of them. And we can do a thing, like we can say fiddle.dl unwrap, and that'll actually cast the literal. That'll give us the value back. So we can say like that. And now we can see, okay, so this address goes to hello, and this address goes to world. And again, these bottom 3 bits, 0. So we're able to tell this is a heap allocated object. And I mean, okay, yeah, so that's that. Anyone have any questions about heap allocated, like tagging? Tag, you're it? Okay. If there's no questions about this, I'm going to move on to something which we definitely don't have time for. I wanted to look at, like, the next thing I wanted to do is I wanted to start passing parameter types. So we know, like, this is a good segue here. If you have this put object here, like, we were able to see, oh, this thing ended in three zeros, so we know it's a heap allocated object. Or it ended with a 1, so we know it's a fixed, we know it's a fixed num. Or it is equal to q true, so we can detect what type it is. And we know, like, okay, when we push onto the virtual stack, like what is the type of the thing. So we'll say, hey, we're going to push that type on. So we can say like p literal object name. So if we run this, it says that these are both unknowns. So we'll just treat those as unknowns. But if we change this to like 1, 5 plus 2 again, if we run this, 21, that's because 21 maps to t fixed num. So we could say like, is this a t fixed num? Why, yes, indeed, it is a t fixed num. Now, unfortunately, like when we do, if we say like def add things, a comma b, a plus b, and then in here we did add things, 5 comma 2. As I was showing in the slides, if we disassemble this, let's just disassemble it so we can see, comment that out. So right here we have a put object of 2, put object of 5, so we know that these two are integers. But when we do this get local here, it doesn't know what the types are that are passed in. So I'd really like to be able to say, like, in the callee, oh, what are the types? So I got to end here in about 5 minutes, but let's see if we can get those types into the callee. So when we do a push, so this push here, actually, let's take a look at the stack after we do a push. And for now, you know what I'm going to do? I'm going to change this to that so it's easier to read. Let's do that. So let's do like where p temp stack. Let's print that out. So if we run this, we got to actually compile it. So if we run this, it's very, very difficult to read here. But here we go. We have a type, which is t fixed num. So we can see in the temp stack, hey, we pushed 2 fixed nums onto the stack. Now let's find in here, like when we do def, let's do opt send without block. So I'm looking at opt send without block because we do a push 5, push 2, then we do an opt send without block to add things. And that just calls compile send, and compile send does what? Compile send will compile our thingy. Let's look at the stack in compile send. All right, q.temp stack. Okay, the compile send, if we print that out, this only happens at runtime. Hold on a sec. We got to do like jit.enable. So if we do foo, so if we call foo, it's gonna, we also, yeah, that should work. Ooh. This seems not good. Something is broken. Huh. Not sure what this exception is about. Anyway, what is that exception about? Let's try this again. I mean, this should work. Oh boy, seems like we got a bug. Anyway, why? What is happening? I'll have to debug this later. Anyway, we saw like right here, if we print out the temp stack inside, like when we're calling into that next method, we can see, okay, we've got a fixed num here and another fixed num here. And the idea is down here, we look up that method we're going to call into, the callee. So this looks it up, and then we try to compile it. So in this case, we're going to be compiling an iseek. So this is where we'll do it. We're actually going to compile that function. So we can say p compiling. So if we run this, man, I got to fix that bug. What is that bug? Anyway, we see this compiling, and that's compiling the callee. So what we want to do is we want to take this stack. Actually, I think this is a good place to end, but we want to take this stack, basically copy it and send it down to the next instruction sequence and say, hey, these are your parameters. So the way that these control frames work is let's just print out the instructions for this. So the callee says, hey, I'm going to push 5 onto the stack, then I'm going to push 2 onto the stack, then I'm going to call opt send without block. And the stack in this callee, so let's do here, the stack for the callee becomes the locals, or the stack for the caller becomes the locals for the callee. So this stack here, 5 and 2, become the locals in here. So as long as we take that temp stack and pass it down to the compilation process for the callee, then the callee should be able to detect the types and then specialize based on those types. So I think I'll do that in a couple weeks after RubyConf, or maybe I can get it done before then. I'm not sure. If I get it done before the next stream, then I'll talk about it in the next stream. But anyway, thank you all for coming. Happy Friday. Ah! Oh, how do I? Okay. All right. Bye, everyone. Oh.